Okay. So first let me thank the organizers for their invitation to speak at this school. Actually, I should say I received the invitation twice. And the first time when I received it, I have kindly refused it. Not refused, but I kindly thanked. But I said that my work, properly speaking, does not really belong to the theory of foliations. And so I was very hesitant to speak here. And then the second time, when actually Christine Laurent was visiting me, we just learned of the tragic death of Marco Brunella, who was supposed to speak. And at that point, I somehow could not refuse the second time, so that's why I accepted. So this subject which I speak about is about, as the title says, non-singular holomorphic foliations on Stein manifolds. But actually, it is more or less, the main gist of this work is more or less about the theory of holomorphic submersions from Stein manifolds. So in fact, I'll present you the proof of the construction of so-called non-critical holomorphic functions, so holomorphic functions without any critical points on Stein manifolds. And then the so-called H principle, the homotopy principle for the theory of holomorphic submersions from Stein manifolds to Cn in particular, and also to some other complex manifolds. Of course, any time you have a submersion, you also have a foliation, since you just have a level sets of this submersion. And this foliation is non-singular, of course. Locally, every foliation is such, but globally, this is rather rare property of a foliation, that it would have like a global potential. So they are rather specific foliations. On the other hand, we obtain some further results, which are not just, they're also in the same scope, in the same framework. There will be some results about foliations given by closed, but not necessarily exact, holomorphic one forms. So those are a bit more general. And also, there is a result about some sort of foliations, still non-singular, which arise by somehow from vector bundles that have flat connection on them. So from flat vector bundles, and then you take sections of these vector bundles over Stein base, and these sections can be made transverse to the foliation upstairs, and so by pulling down you get foliations downstairs. So those are also more general than just submersion foliations. And then there are several open problems in this direction. In fact, as I'll tell you, the key open problem, which was for me the motivation to start this work, is still open. I still couldn't solve it. The so-called H principle in the top dimensional case. Okay, I should say all of this work is, not all, but most of this work is by now about 10 years old, so it's not terribly new. But there are some more recent things. So those things I'll tell you at the end, or perhaps since a few years ago. Also, I should apologize that I'm not planning any lecture notes for this series. And that's for two reasons. One is that I'm too busy. The second one, the better one, so the first one is that I'm lazy. But the better one is that actually everything I'll tell you is written in this book. So let me write the title of this book. So it's a book which by myself, which was published last year by Springer. So the title is Stein manifolds and holomorphic mappings. And it was published in the Ergebnisse series. Dritte Reihe, volume 56. So it's Springer 2011. Now, unfortunately, as you know, these books are not cheap, and they're not, so certainly don't wish to sell you the book. However, I can say the following. Also, I'm unable, because of the copyright, to just freely give you copies, even for this conference. However, if you are at a university, at any university which subscribes electronically to this series, you can actually just download the chapters for free. So maybe, I don't know, I asked Christine to check if this university can be done, but we can.
I had no time to.
You had no time, okay.
I have to verify what is the type of connection.
Okay, so anyway, if a university subscribes to this series electronically, then from any computer tied to this university, you can actually download the PDF files and print them of individual chapters. And I'll let you know as we go through where is essentially what I tell you is a union of some sections of this book. This book is not so much the main gist is actually the so-called Oka-Grauert-Gromov theory. But in fact, the techniques which I'll expose here are more or less the same. I mean, very similar to those which are used for the Oka-Grauert theory. Okay. By way of apology, I should also say that for 2 nights in a row, I slept extremely poorly because the apartment where I'm staying is too warm. And that means my powers of concentration are seriously diminished, and the lecture will probably be worse for that, and I apologize in advance. I hope that this will improve the situation. So let's start with some basic definitions. So if X is a complex manifold, then and if we have a compact set in X, so first I start with some, maybe I should say that the first part of my lecture will be about Stein manifolds. And also main results. So this is more or less today's lecture. So this is the first chapter of this lectures. And today I won't be able to prove very much yet. We'll go through results and indicate some consequences. And then in subsequent lectures, I will go through some of the most important parts of the proof. So if we have a complex manifold and K is a compact set, then recall that the envelope K hat with respect to the family of holomorphic functions on X is just the set of points where any holomorphic function satisfies the maximum principle. So f at point X is less or equal than supremum of f on K. Let me just write it like this. So this is supremum of f, of values of f on K, and this should be true for each f holomorphic on X. So this is called a holomorphically convex hull of the set K in X. If X is Euclidean space, then this is the polynomial hull. And we call a complex manifold holomorphically convex. This is a definition if the envelope, if this hull of any compact set is also compact. So if K hat is compact for each K compact. For each K compact. Now, this can happen, of course, for trivial reasons. For example, if X itself is compact and connected, then you have no functions on K on X other than constants, and so the hull is always equal to all of X, and so it's compact. Okay, but these cases we won't consider. We'll consider rather manifolds which are open. In that case, this is a non-trivial property, and this property probably goes back, I don't know when it was first discovered, but certainly you have a theorem from 1932 due to Cartan and Tulin, which says that if X is an open set in a Euclidean space, then X is a domain of holomorphy if and only if X is holomorphically convex. So recall that domain of holomorphy. I'm sure you're all familiar with this term. This means that, so you have a domain, open set, and this means that for each boundary point, you can find a function holomorphic on this domain which you cannot continue anywhere across this point. But then it can be shown, it's shown by them, that in fact then you can find one function that you cannot continue anywhere, and they show that this is equivalent to this being holomorphically convex. After that, so the same, actually the same holds for domains, for so-called Riemann domains, a bit more general class of sets than these open sets in Cn are the so-called Riemann domains over Cn. Okay, what is a Riemann domain over Cn? So you have a manifold, a complex manifold of dimension n and a holomorphic map F with some components to Cn, not onto, but just to Cn, such that this F is locally biholomorphic. Okay, so any such complex manifold which arises, and such things arise very naturally by analytic continuation. So if you take any open set in Cn and you just take all holomorphic functions on this domain and then you analytically continue them, you get, of course, upstairs a possibly non-Schlicht domain and a map downstairs such that all functions from your original domain, maybe your original domain was something like this, and then you can embed this domain, which is not a domain of holomorphy. You can embed it as a copy, as a biholomorphic copy upstairs, and you get this bigger thing. So for this thing, there is also a notion of when is this a domain of holomorphy, and the same is true, but here you have to add one more condition, namely the condition is that points in the same fiber of F are, those points are not separated by functions on the base. So you should add also, so you must add that holomorphic functions on X separate points. So this means for each two different points, you have at least one function that has different values at these 2 points. So if you add this axiom and you add holomorphic convexity, then you again have characterization of such things. So if I continue historically, there was one more key result, and then I'll give you the definition. So the result published in 1949 by Benke and Stein tells that every open Riemann surface X is holomorphically convex and OX separates points. So this was a very key result. I learned from Remert that actually this is a much older result, maybe from during the war. But because of the war conditions, it was only published in 1949. It's a result by Benke and Stein. And I think that this was what led Stein. So here we have now a definition. Karl Stein. In 1995, he had an important paper in which he treated the so-called second Cousin problem. So he had some very interesting results on the second Cousin problem, which really means holomorphic line bundles. And in this paper, he posed the definition that a complex manifold X is holomorphically complete. But these were his words, and today we just say it's a Stein manifold. So a Stein manifold, if, so we have two axioms, A, X is holomorphically convex, and the second axiom is that holomorphic functions separate points. And then actually there was a third axiom, which I'll put in parentheses, which is not needed. The third axiom, which he originally proposed, was that OX provides local charts. Okay, so what does this mean? This means that if you take any point of a complex of your manifold, then you find, well, by definition, in a neighborhood of a point, you have a chart, meaning that you have a biholomorphic map F to some neighborhood of the origin in Euclidean space. Okay, so you have such a chart. But so the crucial property of a chart is that the differentials of the component functions are independent. At a chosen point. But here Stein asked that such local charts be provided by global functions. So that means for each point there are n global functions holomorphic on your manifold such that their differentials are linearly independent. These are complex differentials at the point x. So they provide the chart. It was later shown by Grauert, 1955, that the axiom C is actually a consequence of B and A. So A plus B implies C. Actually, vice versa is true also. You can replace axiom B by C. You can just take A and C, and this will imply B. So it's also true that A plus C implies B. So you can choose any of these two. Moreover, Grauert studied, this I will not need, but I just mentioned, Grauert studied much more general situation when X has singularities, so so-called complex spaces. And he showed, he used the same two axioms on complex spaces, and that's a notion, that gives a notion of a Stein space. Stein space with singularities. Okay, mostly we will not need this theory of Stein spaces, so let's just stay at this. Okay, and then after that came, so let me see that I didn't skip something important. Okay, here I have a list of examples, which I will skip for now. But let me mention, I'm mentioning some things which are well known, but I want to mention them because I will use them very much later on. So there are other key characterizations of Stein manifolds, of the class of Stein manifolds. So I'm mentioning those characterizations which we shall strongly depend on later on in the course. So one is that well, if I go historically, then I should say that the first one was proved in the seminar of Henri Cartan in the years 1951, well, 50 to 52, around 1951. So not just by him, but by members of the seminar. And that is that a complex manifold X is Stein if and only if it has vanishing cohomology This one I actually won't need so much, but occasionally I'll use it. So it has vanishing cohomology groups. You can think of these as being Czech cohomology groups. Sometimes this is written with a check here. For all numbers q bigger or equal to 1, and f is any coherent analytic sheaf. So any coherent analytic sheaf over X. Okay, so key examples of such sheaves are, for example, the sheaf of holomorphic functions itself, any ideal sheaf of a complex subvariety, and so on. So coherence really means that such a sheaf is, first of all, let me just say by words to remind you what is a coherent sheaf. So first of all, this should be a sheaf of holomorphic modules. So this means, so this is sheaf of O modules. O is OX. So this is sheaf of structure sheaf, the sheaf of holomorphic functions on X. So this should be sheaf of OX modules. And this sheaf should be locally finitely generated. So at each point you should have finite number of sections that generate each stalk. And then also when you look at the sheaf of relations between these generators, it should be also finitely generated. Okay, so I won't enter too much into that. Let's see, where is the, I don't see the eraser. Can you point me to an eraser? Okay. Perhaps it's hidden by my, yes, thank you. Yes, I successfully hid it, thank you. Okay, so let me erase these two lines. Okay, the characterization that will be, that's somehow more important to us, came in around, so Remmert, 1956, and then more decisive results by Bishop and Narasimhan around 1960. And they show that X, a complex manifold of dimension n, is Stein if and only if X can be embedded properly holomorphically into a Euclidean space. So there exists a proper holomorphic embedding. So this just means that you can see X as a closed complex submanifold of a Euclidean space, and in fact in their results you could take n to be 2m plus 1. So this 2m plus 1 would be just like Whitney's result for embedding smooth manifolds into Euclidean spaces, except Whitney's theorem says that every smooth manifold embeds into this Euclidean space of this dimension. In the holomorphic case, this of course cannot be true, since these have a lot of holomorphic functions, obviously, since you can restrict functions on Cn to them. And in general, you can't expect too many holomorphic functions on a complex manifold. Okay, so this shows that somehow Stein manifolds are holomorphic analogs of affine algebraic manifolds. There is a much more interesting and better result, which let me mention here, since I won't talk about it later. It's from 1992, Gromov and Eliashberg. They actually show that this n can be improved. This is not a good bound. Actually, you can embed Stein manifold of dimension n to Euclidean space of dimension 3/2 of n, integer part plus 1. So roughly 3/2 of n, integer part of 3/2 of n plus 1, if little n is bigger than 1. And okay, so if you don't have a open Riemann surface, if n is 1, then this is an open Riemann surface. So X is an open Riemann surface. And in such case, this number would be 2, obviously. And so it's a question whether you can embed each open Riemann surface in C2. This is still pretty much open. You can do it in C3. That's already by this old result, since 2 times 1 plus 1 is 3. So by the old result of Bishop and Narasimhan, you can embed it in C3. In C2, the problems are, of course, self-intersections. You can immerse it properly into C2. There is no constructive way of getting this resolved. While we do have many recent results on this, which are also described in my book about existence of embeddings in C2. But in general, this problem is open. Okay, so this is the second characterization. And then finally, the third one which, let me actually write it here. I'll erase a part of this, it's inessential. So the third characterization, which for us will be very important, is due to Grauert. He has several papers, but I think the decisive one is a paper from 58. In this paper, well, also in 58, he has many papers, but in this paper, he proved that X is Stein, a complex manifold X is Stein, if and only if there exists a function rho, a real function, with values in R, union infinity, not just in R, I'm sorry. So a real function X, you can say, you can go to R plus if you like, such that rho is an exhaustion function. So exhaustion means that sublevel sets are compact. So this means sublevel sets rho less than or equal to C are compact for each real C, and such that this function is strongly plus superharmonic. I think Professor de Mailly spoke about this yesterday. So the condition is that ddc of rho, which is the same as 2I dd bar of rho, is strictly positive. Okay, so such function is called strongly PSH, plurisuperharmonic. So in our analysis, we shall strongly use this. So the in locally, you remember from yesterday's talk, I suppose, that this form is actually given by the Hessian, by the complex Hessian. Okay, I'll say more about this when I come to use it. Okay, so these are three main characterizations of the class of Stein manifolds. Okay, now I wish to go to some results, because now I have this general stuff set. Let me still continue on the same blackboard, since I want to leave the results on the board for a while. Okay. Okay, so let me now talk about non-critical functions. So perhaps this was section 1.1. So let's now talk about 1.2. Okay, so we should be interested in finding functions f from our complex manifold such that the differential of this function, so we say that f is non-critical if differential of f at x is non-zero for each x. And if it is not non-critical, then critical point is point where differential vanishes. So x is a critical for f if differential of f vanishes. Of course, in local coordinates, the equation for such points is just you have f, let's say, so in local coordinates, you have z, z1 up to zn on somewhere on x, and this equation is just that partial derivative, so differential of f is just summation of f with respect to zj times dzj. So the equation for critical points is that partial derivatives are all zero. So this is equation of for critical points. And okay, so these are n holomorphic equations. And since you are on a manifold of dimension n, so you can expect that if you have lots of functions, in particular if x is Stein, then for a generically chosen function f, since the zero set of each such equation is a complex hypersurface, so you intersect n complex hypersurfaces. So for generic f, this intersection should be transverse. And so points where this happens are isolated. So these are isolated points for generic f. Now, of course, if you're on a Euclidean space, you have lots of non-critical functions, in particular linear functions. Linear functions are non-critical, but already if you look at holomorphic polynomials, then they are very rarely non-critical. You can get other examples of non-critical functions. But let's observe now that so there are many, let's say there are many non-critical functions on Cn. And as a consequence, if you have a Riemann domain, then you also have, then by definition, so if this is a Riemann domain, then by definition this means that the differentials of the components of f satisfy this equation. Okay? So this means in particular not only does each differential vanish, but even they are linearly independent. So this means you have also on x, these functions are non-critical, and therefore each non-critical function of course gives you a non-singular foliation in the base. For example, you can just take so if f is non-critical, then the foliation f equal to c, or c in c, let's call it f, has smooth leaves, smooth holomorphic leaves. So it's a non-singular foliation by hypersurfaces, by complex hypersurfaces. Okay, so these are just obvious remarks. So in particular, if you take downstairs, for example, the holomorphic foliations by coordinate functions, like that, and then you pull it up to your x, you get upstairs a similar picture. Okay, and then the question which is still open, and which was actually the motivation for this. Okay, let's observe one other thing. Let's observe that in such a case, when you have a Riemann domain, so you have this condition satisfied. So in this case, the differential of the map f induces a trivialization of the tangent bundle of x. And by the way, you can think of this as a real tangent bundle, but I'm going to identify it canonically with a 1,0 tangent bundle of x, which is a holomorphic bundle. So I'll think of Tx as a holomorphic complex vector bundle of rank n over my manifold. So induces a trivialization. So this is just by definition. Okay? These two things are the same. And now we have trivialization, meaning a map to C cross x cross Cn, which of course is obvious. I mean, you take a point and a vector, and you just map it to the point and the differential of f at x to this vector, which is then a vector in Cn. So this is obvious. So if you have so that means if x to f to Cn is a Riemann domain, then df induces trivialization. So this means tangent bundle is trivial. And so the converse, so the problem is whether the converse is true. Okay, Okay, so what's the converse? So the converse is if you have a complex manifold, so if X, actually let's pose it in Stein manifold. So if X is Stein, and if Tx is trivial, the question is whether this implies that X is a Riemann domain over Cn, i.e. there exists f from X to Cn satisfying, let me call this condition star, satisfying the star condition. Okay, so this question is still open, and this was my motivation. As far as I know, this problem has been open from the 50s. All of these things were considered at the same time where the basis of Stein manifold theory were put down. And there are very few examples when the answer is known, even up to now. Okay, at some point, I guess Gromov got interested, Misha Gromov got interested in these problems. And if you read his book, oh, by the way, let me make a comment here. The question is, what do we mean by this bundle to be trivial? Of course, we can mean two things. This is a holomorphic bundle, as I said, holomorphic vector bundle. So in particular, it's a topological complex vector bundle with a holomorphic structure. So to be trivial can mean topologically trivial, meaning that you would look for a map like this, which only depends continuously or perhaps smoothly on the base point. But it's, of course, linear on fibers, C-linear. And the second thing, the stronger notion, is holomorphically trivial. So that means the map should be, like in this example, holomorphically depending on X. And it is known that these two things are the same. So this is a so-called Oka-Grauer theory. So this comes from around while Oka had a result in 1939, but then Grauer did most of this work in 1958, 57 to 58. So this theory says that it says, roughly speaking, like this: a special case that over Stein manifolds of Stein spaces, the topological characterization of complex vector bundles coincides with the holomorphic classification. This is true for in much more general case than for vector bundles. It's true for example, principal bundles with Lie group fibers, complex Lie group fibers. So cohomologically, you can say that the group. How do you measure the classes of topological vector bundles of some rank? You look at Češ cohomology group of your manifold with coefficients in the sheaf. Let's say if I start with the holomorphic first. You take the sheaf of holomorphic maps from X to the general linear group, because this is the structured group. Let's say K, C. So this is the group of K by K invertible matrices. So this sheaf means you take sheaf of germs of maps from X to the group, because these are transition functions in your bundle. Okay, and there is a natural map of this group to the group where you replace O by C by continuous maps from the base to the general linear group. Okay, and this map is an isomorphism. So this is how you can state this result. And this I'll use very frequently in the lectures. This is also, you can find this in chapter 5 and then chapter 7 in my book. Okay, but let me return now to Gromov. I was going to say that Gromov, in fact, looking at this question, well, in particular, in his book, published in 1986, is a book called Partial Differential Relations, also in the same Ergebnisse series. So he asks two questions. Question one is, does every Stein manifold admit a non-critical function? Since if you want to answer this question, of course, then you have to come up with many non-critical functions, at least in the case when tangent bundle is trivial. So he asks, what about in general? And then he asked a more precise question, which is this one we shall answer, but the second question is still open. He says, how about the following? Let's take a vector field. So let's say that L is a nowhere vanishing holomorphic vector field on X, which is always Stein. Okay, so what could you ask in this case? In this case, the flow of this vector field induces foliation by leaves. So the leaves are complex. So you have leaves of L. So trajectories of L, so you have foliation. And then he said, is there a function holomorphic on X such that L applied to this vector field is never 0? So what does it mean? It means that if you restrict, so F, so this is in X, F goes somewhere to C, F goes to C. And so this equation, LF non-zero, means that when you restrict this F to any leaf, and the leaf is just an open Riemann surface, so you restrict it to a leaf, it should be non-critical on the leaf. So it should have non-zero velocity at each time on the leaf. Okay. Well, here I'll give you an exercise. The simple exercise is show that one cannot solve the equation LF equal to some given function. For example, LF equal to 1 in general. So you can come up with, even on C2, say on C2, you can come up with first examples of non-vanishing vector fields, nowhere vanishing, such that there is no function f that would satisfy the equation LF equal to 1. To my knowledge, this problem Q2, question 2, is open even if X is just Euclidean space and L is an algebraic vector field. So this means something with algebraic coefficients. Okay, so this is open. So Q2 is open even for algebraic vector fields on Cn, to my knowledge. Maybe somebody who knows more about foliations knows something about this, but I asked several people and I don't know the answer. However, we have an answer to, an old answer to this question. You see, if you're on an open Riemann surface, then you can find such a function. So there is an old result, which let me also write here, is an old result by Gunning and Narasimhan, that if X is any open Riemann surface, so this means a one-dimensional Stein manifold, open Riemann surface, then there exists a function f on x holomorphic such that df is nowhere 0. So this question Q1 has a solution on Riemann surfaces, on open Riemann surfaces. Open means non-compact, of course. And in this case, the proof is not very difficult, because in this case what you do is you just you just find f. Actually, you find f whose differential is of this form, that you find some suitable function g, holomorphic, such that e to the g times, so you start with some nowhere vanishing holomorphic 1 form. So you start with an nowhere vanishing holomorphic 1 form. Why does such a thing exist? Such a thing is a section of the cotangent bundle, but it's a known result that on Riemann surfaces, on open Riemann surfaces, every line bundle and every vector bundle is trivial. So you have such a thing, such a nowhere vanishing holomorphic 1 form, and then you simply find a multiplier for some holomorphic g. So the purpose of this multiplier is to change periods of this form to 0. The problem why the crucial point is that on Riemann surface every such form is closed. So this is automatic because you're on a Riemann surface. In higher dimensions, this is a highly non-trivial condition for form to be closed. But on a Riemann surface, this is always true in dimension 1. The only problem is that when you integrate this form along loops, so if C is a loop, then it may have non-vanishing period, and this prevents the form from being exact. But then they find such a function such that e to the g kills the period, so it makes all periods 0, and after that you just get f by integrating this form. So f is then just integral from some initial point to some variable finite point of e to the g omega. Okay. All right, so this is where the status of the theory was. Now, this is where the status of the theory was when I got interested in these questions around 2000. Okay, so now I can state the first theorem. So this theorem says that actually the answer to Q1 is yes. Okay, so we can say as follows. So let X be a Stein manifold. Okay, then first of all, there always exists a non-critical function. And we can say more precisely, then there exist functions f1, f2, up to fq, holomorphic on x, for q being the following integer. It's the integer part of n plus 1 over 2. So it's roughly half of the dimension of x. So I can find holomorphic functions, this many, such that df, such that their differentials are nowhere 0 at each point. So they are nowhere 0 on x. So this means these functions are non-critical and have linearly independent differentials. So in particular, there exist always, and there are many such. We should see there are many such. There was an old example which I will also try to explain in the sequel, maybe next time. It was an old example due to Forster from 1971, if I remember correctly, but this example is, so this example shows that this number is the maximal possible in general. For each n. So that means for each n, I can find the Stein manifold with a property that, in fact, there is no mystery to this. It's just that if you have that there exists a Stein manifold, so for each n, there exists a Stein manifold whose Chern class of index n over 2 integer part is not 0. And then one can see that for any such manifold, so his example, his concrete example was the following, that you take first a Stein surface, let me call it y, and this Stein surface is just the set of points. For example, you can take the set of points z0, z1, z2 in a projective plane such that the sum of the squares is not equal to 0. So you take a quadric, you take a simple quadric out of CP2, out of the projective plane. And this turns out to be, it's easy to see that this is a Stein domain, so it's a Stein surface. And then you take X to be either this Stein surface to some Cartesian power m, if the dimension of X should be 2m. So if you have even dimension, you just take appropriate power, Cartesian power of this particular surface y, and then you take this surface to power m, and then just cross multiply with an extra copy of c if n is 2m plus 1, if n is odd. So we will see that this particular example has, one can see that it has this property, and this property will then show that you cannot have more than this number of independent differentials. Okay, so this is sort of one main result, but we have additions to this result. Additions are, in the Stein theory, you have the usual, this Cartan theory, which tells you that if you have such a configuration, let's take, I take a compact set, holomorphically convex in our X. So X is my Stein manifold. I take some compact holomorphically convex set, and I take some subvariety. Let's call it X prime. Okay. Okay, so we have K compact holomorphically convex, and X prime closed complex subvariety of X. And let's assume that you have such a collection of functions. Well, let me just state for one function. Okay, so let's say just for q equal to 1. So let's say that f is, let's say that u is an open neighborhood of this configuration. So just some open set containing this picture. And let's say that I have a function f holomorphic on this set, on this open neighborhood, whose differential is nowhere 0. So whenever I write this, I mean at each point. It's a pointwise condition. Okay, then there exists a function, let's say capital F, which is again over 0. I mean, differential is over 0, so it's non-critical, and which matches F exactly on x prime on the subvariety. So F equals to little f on x prime. What about on k? On k you can approximate. So you can say that f minus little f on k is less than some given positive number. So for each positive number, so you have these three conditions that you can match. And it's so if you don't look at this condition, then this is standard. It's a standard result in Oka theory. I mean in Cartan theory, that in a Stein manifold you can approximate holomorphic functions on such sets. This is some kind of Runge theorem. It's actually called Oka-Weil theorem in the context of Stein manifolds. And then you have the so-called Cartan extension theorem, which tells you that each function holomorphic on a subvariety can be extended to a function on all of x. So without the non-critical condition, this is very, very standard. This was known from the 50s. So the addition here is this one, of course. You can keep this condition. And there is the same statement. I won't state it again for several functions. So it's the same statement. So same statement for f, which is f1 up to fq, map from x to cq. Of course, with q less or equal than n plus 1 over 2. Always this bound. It's the same statement. Okay, so what does this kind of thing gives us? You see, it gives us submersion foliations. So note let me perhaps state this as a corollary. Yeah, okay. Before I go to corollary, let me state one other related result, which is not a formal consequence, but which one proves with the same methods. So maybe you are unhappy with, certainly people in foliation theory are extremely unhappy with non-critical foliations. They say they're not too interesting. Interesting things happen at critical points. So I'd like to produce for you something more interesting, therefore, and say, yes, not only we can make non-critical functions, we can actually solve Mittag-Leffler problem for critical points. So what should Mittag-Leffler problem mean? Mittag-Leffler problem is usually that you want to prescribe something at a discrete set of points. For instance, poles of a meromorphic function, principal parts, or things like that. So here we also have the following theorem. Let me actually number these theorems. So let's call this theorem 1. And then let's just call this one theorem 1 bis, because it's really not a new theorem. It is just a little improvement in the proof. So in this theorem, we can, for instance, say, so again, x should be Stein. And let's say that I have some discrete set of points. Let's call it P. So P is P1, P2, etc. So this is discrete. Inside X, so we have some points. Okay, let's draw a few points here. P1, P2, P3, etc. And then I will have some neighborhoods. Let's say U1, U2, U3. So these are open neighborhoods, and in each of these neighborhoods, I have a function. So let's say I have function F1, F2, F3, etc. So for each j in n, let fj be a holomorphic function in an open set which contains Pj. So think of Uj to be small open set in X. And I assume that F has the only critical point, say, here. So such that Pj is an isolated critical point of Fj. Elsewhere I don't care. So differential of Fj vanishes at P1 and then doesn't vanish in some neighborhood. So I could, by shrinking Uj, I could as well say that Pj is the only critical point, okay? Okay, then I can produce a function, a global function, on X, which has precisely these critical points, and actually which match these Fj's as much as you like. So let's say given integers nj, possibly large, given integers for each j, there exists F holomorphic on X such that it is not non-critical, but such that its critical locus, let me just write it like this, crit F, so this is the set of points X where differential is 0. So this is exactly P. Okay, and you can ask that the difference F minus Fj vanishes to order nj at Pj. So you can have any order of vanishing. This means that F agrees with little Fj as much as you like at these points. Okay. So this creates functions for you. So basically you can say if I want to prescribe a foliation locally, so the level set here may be singular, then nearby you have nice level sets. You have this kind of picture. Okay, similarly here you have a complication at this point, but nothing near. Okay, and then you can produce a global foliation which more or less looks like this. I mean, more or less. So it's not, you cannot say that it's conjugate to it or anything like that, but still you have this high order vanishing as high as you like. So you have very much this picture. And even this can be slightly improved. For example, into this you can superimpose these conditions. So in addition, I can throw in a subvariety, a holomorphically convex set, etc., and join these two things together. It is still true. So that means if these Fj's would be defined somewhere and on a subvariety also in a coherent way, then you can satisfy all these criteria. Okay, so this is pretty much the story about the first theorem. Now let's look at some corollaries. Okay, so let's stay for the moment in the case of codimension 1. I guess I cannot erase the second blackboard, right? So now I'm stuck with this. I have to erase something. All right, let's erase here. Okay, so let's look at some simple corollaries for hypersurface foliations. And then next time I will, or perhaps I can start today. I finish at 10, right? Yes. Okay. And actually 10 by that clock. So, which is 5-minute difference from the two clocks. Okay, so let's look at some corollaries. Let's say that this is 1.3. Corollaries concerning hypersurface foliations. Concerning, let's just say foliations. Corollaries concerning foliations. Let's start with simple ones. So the first corollary, let's call it C1. is, for example, the following one. Let's say I just draw a picture. I have this picture, so let V in X be so X is always Stein, and V is a closed complex submanifold of my Stein manifold. So let V be a closed complex submanifold in X, which is Stein. Okay. Then there exists a holomorphic foliation by hypersurfaces which looks like this. So it's non-singular and it's everywhere transverse to V. So then there exists a non-singular, that means without critical points, holomorphic foliation of X, let's call it F, by hypersurfaces which are everywhere transverse to V. Let me just write this with the usual symbol, F transverse to V. So this means that if you have any leaf, let's say if sigma is any leaf of this foliation, everywhere where it intersects V, transversality means that the sum of the tangent spaces is equal to all of the tangent space. So the tangent space to V plus the tangent space to the leaf span, are equal to the tangent space of X at that point. Well, not general foliation, no. Let me show you. The proof is really trivial. The proof is really trivial, but I extend submersion foliation. So basically, the proof is essentially just one line. First of all, we notice that V is Stein itself, because it's a complex submanifold of a Stein manifold. Such a thing is Stein. So therefore, there exists F holomorphic on V, non-critical. Okay, so this F determines the foliation on V. And this F exists by the theorem, which I stated before. But now, this addition, not this one, but the one here. The one here. Okay, this function is non-critical, so also in some, I can extend it to some neighborhood, so it's non-critical there. And then this theorem here, this addition, tells me that now I can extend F to X. So by theorem, there exists F, which is nowhere critical, such that F, capital F on V matches little f. And then you just take F to be the foliation you take to be the level sets of this F. So it's F equal to C. Okay, so it's really obvious. So I'm extending submersion foliation to submersion foliation. Okay. Okay, now another one is the following. That I can make such a thing a leaf. Well, if V is a, let's say if V is a hypersurface, I can make it into a leaf. So corollary 2, if V is smooth, by smooth I mean without singular points, complex hypersurface, here I think I need some conditions. Let me check. Yeah, let me check. Yeah, okay, so here I need, if V is a smooth complex hypersurface in X, which is Stein, but here I need a trivial normal bundle with trivial normal bundle So recall that the normal bundle of V in X, I just call it like this, is simply the tangent bundle of X on the manifold, restricted to the manifold, and then you quotient out the tangent to V. So if this trivial, so I'm requiring that this bundle is trivial. Okay? Then there exists a non-singular holomorphic foliation f of X by hypersurfaces. So it's just called hypersurface foliation, such that V is a union of leaves. If it's connected, it's just a leaf. Otherwise, it's a union. It's a union of leaves. So I'm saying if here is my V, then I find foliation like this, which contains this one as a leaf. Okay. Now let me remark that this condition is, of course, always true. So note that n Vx is always trivial if basically this is an element of the Picard group, right? It's a line bundle. It's a holomorphic line bundle on V. So it's trivial if the second cohomology group of V with integer coefficients is 0, because you actually have an isomorphism in such case between the Picard group, which is the group H1V O star. So this is the group of holomorphic line bundles on V, and the group H2VZ. This comes from just the exponential sheaf sequence plus the fact that V is Stein. Okay, so as soon as you have this is true, notice also that in the hypersurface case, it's actually true that this normal bundle, which is initially just bundle on V, actually extends to a line bundle of all of X. And this is just because you think of it as a divisor. You think of V as a divisor. So you define V by local holomorphic functions vanishing to first order. And on the complement of V, you just take function 1. So this cocycle gives you a line bundle. And this line bundle is on V is precisely the normal bundle. So this means, since you can extend the normal bundle to X, so this tells you that if it happens that H2X V is 0, then it's also true. So let me just say here, or if H2X Z is 0. This is because we can extend line bundles. For example, if X is Cn. So if X is Cn, then this is always true. Each hypersurface is a leaf in a foliation. Okay. So how do we see this? Well, we have to just use the Grauer's tube, right? So we use so proof is we use the result of Dokia and Grauert that let me just draw a picture. So here is my V, and this is this theorem is true not just for hypersurfaces. It's true anytime you have a submanifold. So let's say if V was a submanifold of some dimension in a Stein manifold X, then you find an open neighborhood or some tube around this. So there exists a U, an open set containing V, and a biholomorphic map, let's call it phi, to a domain omega in a normal bundle. So this is an open set containing the 0 section. Okay, so basically you say that, yeah, so a neighborhood of V in anywhere it's embedded is biholomorphic to a neighborhood of the 0 section in the normal bundle. This, of course, hinges on the fact, this is not hard to prove, but it hinges on the fact that V has a basis of Stein neighborhoods in X. By the way, this is true even if X is not Stein. In this result, you don't need X to be Stein, you just need V to be Stein. X can be arbitrary. And this is thanks to the theorem of Hsu. Because if V is Stein as a closed complex submanifold in anything, then it has a Stein neighborhood. And once you have a Stein neighborhood, you're in the Stein case and you can construct such things. So this is well known. And now simply what I do, so in omega, omega looks like this. Here we're in the normal bundle. So omega is perhaps something like this. And in omega, of course, I have a foliation just by, so what do I need here? Yeah, well, this bundle, in general, this wouldn't be true, but in this case, my bundle happens to be trivial. So it's V cross C in our case, because now we look at line bundle. So this is V cross C. So it's trivial. So I have this foliation by constants. And just take this foliation and pull it back. And I get a foliation here. But that's in a neighborhood. But now you can again use my theorem, which I stated before, because you don't really pull back the foliation, but you pull back the function. So you just take a function here, which has this as level sets, and then you compose it with phi. And you get a function here, which gives you a foliation nearby. But then I stated an improvement of theorem 1, which says that if you have such a function nearby, near V, then you can actually interpolate it. Okay, so let me write this down. Okay, so I start here just with projection to the second factor. Let's call this G. So it's projection to the second factor. I take F to be G composed with phi. So this is now non-critical on a neighborhood of V in X. And it has and V is a leaf of F. Actually, is the leaf F equal to 0, or a union of leaves in general. And now you just apply the theorem to get capital F on X, nowhere differential nowhere 0, which agrees on V with F. And so you're done. You can even make it agree to high order if you like the second order. So you can make the foliation look nearby pretty much like the one you see. Okay, I have about 10 minutes. Let's see. This was the... Yes, of course.
If you go corollaries, do you allow V to have more than one connected component?
In the corollary? Yeah, it should. Yeah, right. It can have one. It can have more connected components. Yeah. Yeah, it works in general. I mean, the theorem 1 bis was stated for interpolation on any closed complex subvariety. It can be disconnected. So I just use that really. So yeah, so it can be disconnected. So in such case, you should understand that V is not a leaf but a union of leaves. Yeah. Okay. So okay. Well, now I have no choice but to go into the perhaps let me check. I have some few more corollaries which concern the higher dimensional case. Maybe I could go into those because I don't wish to start something too new right now. Yeah, but not really. So let's actually go into this. I'll talk more about this next time. Now we can put this blackboard down again. Okay, before I stated the theorem with a certain number q, if you remember. And this obstacle is really topological. So before I told you that if x is of Stein of dimension n, and if I take q to be this number, roughly n over 2, then I can find functions such that their differentials are independent. Yes, and I said before that this is maximal in general. But there are better theorems. So we'll see this very clearly when we get to the proof. Why is this number the optimal one? Because in the proof, of course, the complication will happen at critical points of a strongly superharmonic exhaustion function on X. So we'll go through level sets. We'll essentially construct these objects by some kind of induction procedure through level sets. This means that we'll each time make objects on a little bigger set until we reach all of X. And there will be some kind of complications, but only analytic complications, when you go between non-critical level sets. So when you have no critical points of an exhaustion, their topology doesn't change, and there will be just some analysis to be done to extend. But when you cross critical points, there you really get a serious obstacle, and there this number enters. And we'll see this very clearly. But what is then the H principle? So let me state this as theorem 2. This fits very well into the scope of things which were done in the smooth case by Hirsch and Smale in the 50s, and then by Phillips in the 60s for immersions and submersions in the smooth geometry. So the H principle essentially says that if you want to smoothly or holomorphically perhaps do something, like embed a manifold or submerge it or so on, then if you don't have topological obstructions, then you can do it. In the smooth case, this was well elaborated by Gromov, in particular in his book, which I mentioned there. But in the holomorphic case, this kind of principle, of which Oka-Grauer theory is actually the prime exponent. Or you can also say that Cartan theory, the fact that coherent cohomology in coherent sheaves vanishes, or Stein manifold. That's also an example. So in the complex geometry, it's more or less only true in Stein manifolds. So theorem 2 says this. Okay, so let X be Stein. And assume that there exists, let's say, for some number q less than n, strictly less than n, there exists a surjective complex vector bundle map as follows. So you take tangent bundle of X and you map it to the, let's call this map theta. You map it to the trivial bundle of rank Q. So you want to have a surjective complex vector bundle map. So this means I don't assume, okay, so this means that each fiber is mapped surjectively onto CQ. The dependence on the base point can be only topological, so continuous. But in fact, by the Oka-Grauer theory, which I mentioned before, actually it's true that as soon as you have such a map, then you also have a holomorphic map like this. Okay, then, in fact, theta is homotopic to a map which comes from a differential. So then there exists a homotopy, let's say theta t, from Tx onto x cross CQ, where t is, say, from 0 to 1, of surjective complex vector bundle maps, okay, with theta 0 is our original map, and such that theta 1 is essentially the differential of some map. I'm saying differential is not exactly, well, it's essentially the same thing. So on fibers is the same thing. So theta 1 is the differential of f, where f is f1 up to fq is now really an honest holomorphic map to CQ. And of course, since I'm asking that these are surjective, this really means that that df is surjective, so this really means that it's a holomorphic submersion. So you see, what does the theorem say? The theorem says if I have a surjective complex vector bundle map from the tangent bundle to some trivial bundle of some rank, then by homotopy, always through maps like this, I can change it to an honest holomorphic differential. And this is now true for every q less than n. And you will notice that this condition is in fact necessary. So here I could say this is if and only if. So if you ask if a given Stein manifold will submerge to CQ, then of course its differential is like that. It's one such map. So it's an if and only if theorem. Now you'll ask me, okay, I'm pretty close to the end, so let me more or less end here. Just say that. So let's call this H principle. For holomorphic submersions to CQ. And let me say that there is no reason why this wouldn't be also true for q equal to n. Well, this is open. Okay, and this was precisely the question we started with. Because for q equal n, the question is if Tx trivial, because you see, when q is equal to n, this would just be a trivialization, right? So the question is Tx trivial, does it imply that there exists an immersion which is then a submersion to Cn? In this case, submersion is the same as immersion. And it's a locally biholomorphic map. So this is still open. And we'll also see in the proof where exactly does the proof collapse. So the proof, which works beautifully for any dimension q less than n, totally collapses in q equal to n, in q equal n case. And actually the reason is not topological, but the reason why it collapses is somehow hyperbolicity. Hyperbolicity obstruction arises in the proof, and this is very common in lots of difficult problems in Stein geometry and in complex geometry in general. You have somehow that Oka principle works beautifully until you hit some obvious obstruction. So there is no obstruction to the question. I mean, this could very well be true. In fact, I believe it's probably true. But at the moment, we cannot do it. For 10 years, we cannot do it. And I'll tell you next time that actually this question, I mean, if you use the theory as it stands, then actually this question boils down, it's equivalent to a very simple Runge type approximation question, which I'll state more precisely next time. Let me just say it. So this Runge type question is whether it's possible to approximate locally biholomorphic maps on Cn from Cn to Cn on polynomially on actually only on convex sets. So this means if I give you a convex set in some Euclidean space and I give you a locally biholomorphic map from this convex set somewhere. So this map is not one-to-one, just locally biholomorphic. Can you approximate it on a little smaller set by an entire map that is of the same kind, locally biholomorphic? So we know really nothing about locally biholomorphic self-maps of Cn. I mean nothing. We know some few things, but very little. And this, in a way, is not too surprising because, you know, somehow these questions, if you think a little more, they get related to the Jacobian problem in some way, in some vague way. And since we don't know much about the Jacobian problem, it's not very surprising that we know very little. However, we know quite a lot about one-to-one maps, one-to-one, injective. And that's the theory which is used in all these proofs. That's the so-called Anderson-Lampert theory. Okay, so more about this tomorrow then. Thank you.